Hey Chem 240 students, how's everybody doing? This is the third video for chapter 16. So there's going to be a qualitative section that talks about acid strengths. So there are some trends that you are responsible for in terms of figuring out which acid would be stronger than another acid. So let's go through those trends, and basically a lot of them are related to where a particular element is on the periodic table. So the first trend is going down a column of elements. The size of the element X increases. Therefore, the HX bond strength decreases and the strength of the binary acid increases. So the bigger the ion, right, the bigger the ion that the hydrogen is attached to, the stronger the acid. So hydroiodic acid is stronger than hydrobromic acid, which is stronger than hydrochloric acid, which is stronger than hydrofluoric acid. So those four elements all come from the halogens, which are group 17 in the periodic table. So here they are. If I have an acid made from HF versus HCl, HBr, or HI, which is the strongest? The one that's the largest, the one that's furthest down in the set. And the rationale behind that is the bigger the ion, once the H plus leaves, the more stable the negative charge is that remains behind. In order for the acid to form, the HX has to ionize to H plus and X minus, and it's easier to make I minus than it is Br minus, than it is Cl minus, than it is F minus. So again, the strengths go hydroiodic, stronger than hydrobromic, stronger than hydrochloric, stronger than hydrofluoric. So you should be able to do the same thing in a different column of the periodic table, right? The further you go down, the strongest. So H2SE, hydroselenic acid, should be stronger than H2S, hydrosulfuric acid, which would be stronger than H2O, which would be hydroiodic acid, but we simply call that water. So acid strengths would go in this order. In fact, H2TE, the one that comes from tellurum, would be even the strongest of the four. Okay. All right. Second trend, going across a row of elements, the electronegativity increases um, from left to right, right? So as you work your way across the periodic table, you learn this in Chem 1, as you go across the periodic table, the electronegativity increases. If you remember, what is electronegativity? Well, first of all, fluorine is the most electronegative element on the whole periodic table. So when you go from left to right, you get more electronegative. So electronegativity is when a pair of electrons are shared between two atoms, how who basically hogs up those two electrons. So if you take the example of HF, for example, right, the two electrons in the bond between the H and the F are not shared equally. Fluoride is such, or I better to say that fluorine has the highest electronegativity on the periodic table. So these two electrons really spend the majority of their time over here by fluorine. So this bond is very polarized, where this side of it over here is very negative, and this side of it is very positive, right? So you learn that from Chem 1. So instead of kind of drawing it like that, we could kind of picture it as sort of a naked proton. Looks like a guitar pick a little bit, where here's the hydrogen over here, and all the negativeness is really over on this other side of the molecule. This side being very, very negative, and this side being very positive. Okay, so these deltas here mean a part of a charge, right? Not a whole plus one, but just like a fractional positiveness and a fractional negativeness. So again, unequal sharing of electrons in a bond. If you have a high electronegativity, you're pulling those electrons over towards yourself. If you have a low electronegativity, these electrons are very far away from you, so you're basically electropositive. Okay, so the further you are, the further you are to the right on the periodic table, the stronger the acid. So let's compare three acids that are both in the second period of the periodic table. HF is stronger than H2O, is stronger than um, NH3. In fact, NH3 isn't an acid at all. These hydrogen ions don't want to ionize at all. In fact, it's the opposite. This one turns out, ammonia turns out to be a base, but it's a different kind of base. It's a base because of the lone pair of electrons on nitrogen that we'll learn about. It's called a Lewis base. Okay, but again, if we forgot about that effect, just the ability to rip off these hydrogens, this one's coming off easier than one from here, than one from here. So even though there are three of them, they don't want to come off. Why? Because nitrogen is sharing the electrons equally with hydrogen, so they're not so exposed to be removed. Remember, you're pulling the H off as an H plus. So the stronger the electronegativity, the stronger the acid. Okay, so looking at our periodic table, here's those three culprits. The acid that comes from HF would be stronger than the acid that comes from H2O. That would be stronger than H3N. Good. Okay, next trend. The next trend has to do with oxyacids. So oxyacids are acids of this form. There's an H single bound to an O that's bound to another element. Okay. Sometimes there's on this other element, there's also other O's that are on it as well. But there's always going to be an H bound to an O bound to something else. Okay. So one simple example of that comes to mind is this acid, HOCl. Right? So you guys may remember this one. If I put all his electrons in, it looks like that, right? So that would be a great example of this. This is hypochlorous acid, right? It is the version that has the least number of oxygens in the set. And you remember the set that we learned is HOCl, HO. Let me write it this way. Sorry. Right, when you had to memorize the polyatomic ions and the acids that came from them, you had HClO, which is this one here, okay? HClO2, HClO3, and HClO4. Okay, so these four acids are all of the form that we're talking about here. It's HO, and then the other element Y in our case is chlorine. Okay, so if you just wanted to practice the names again, this one is hypochlorous acid, this one is chlorous acid, this one is chloric acid, and the biggest one, the one with the most oxygen, is called perchloric acid. So in this series, we're going to learn which is the strongest depending on, first of all, what the element Y is, and then second of all, how many oxygens there are in the series. So trend number one. For a series, let me get this guy over here. Sorry about that. For a series of oxyacids with the same structure, the acid strength increases with the electronegativity of Y. Okay, so turns out you can't make the one with fluorine. Okay, it isn't stable. But in the comparison between HOY, where Y is chlorine, bromine, or iodine, the strongest one is going to be hypochlorous acid versus hypobromous acid versus hypoiodous acid. So this one should be stronger than this one, that should be stronger than this one. And the rationale behind it is chlorine is the most electronegative of the three. So you can look up their electronegativity. So in the series, now notice they all have just one oxygen. So we're holding that constant. We're not also putting extra oxygens on it. So which one is the strongest? The one that comes from the element with the highest electronegativity. The O and the H is the same. So you're comparing Cl versus Br versus I. And if you remember the way electronegativity works, the most electronegative element on the whole periodic table is fluorine. The least electronegativity is francium. So anytime you go up and to the right, you become more electronegativity. So here we're going up, right? So if you go up, that makes you more electronegative. So this guy would be stronger than this guy, would be stronger than this guy, would be stronger than this guy. It turns out that you just can't make the HOF version, okay? But of these three, you do need to know this one would be stronger than this one, would be stronger than this one. What do we mean by strength? The ability to ionize that proton. For this to break apart, right? Acid strength is the ability to break apart and do the following. See if I'll write it down for you. It would be HClO aqueous to decompose into H plus aqueous and the counter ion ClO minus aqueous, right? How easily that occurs, right? If this is an equilibrium, this particular reaction goes, how much it goes all the way to the right. Good. Okay, so that's the first set of trends for the binary acids. And then down at the bottom, this is on page 9 of your notes, down at the bottom for the oxyacids. Okay, a couple more trends that you're responsible for. So the second one for the oxyacids, this is on the top of page 10 of your notes. For a series of oxyacids which have the form OHMYON, okay, and I'll fit the last one that we just did into that. The acid strength increases with the N, right, which is the number of oxygens bonded to Y, excluding the O atoms in the OH groups. Okay, so if you look at the example that we just did, right, this one, HOCl, which I have here, and you look up here, there's no extra N's, right? There's nothing extra over here. All of the O's are in the OH group. So this one has N is equal to 0. All right, the next one in the group, HOClO, has got one of these kinds of oxygens and again, one of these kinds of oxygens. So this one would have N is equal to 1. Okay, so carrying on the trend, this one has two oxygens that don't have an H on it. So this guy over here would be OH1YO2. And the last one, this one would be OH1Y, which would be ClN3. All right, so the more oxygens you pack into it in the series, the stronger the acid. So perchloric acid is stronger than chloric acid, which is stronger than chlorous acid, which is stronger than hypochlorous acid. So a simple way to remember that is the more oxygens, right? The more oxygens, everything else being the same, the stronger the acid. Okay. Last one is common sense to me. Okay. So how does this one work? This one works. The acid strength of a polyprotic acid, right? An acid that has more than one hydrogen that can be donated. Protic means hydrogen, right? A proton is a hydrogen ion. So polyprotic means more than one hydrogen. So the acid strength of a polyprotic acid and its ions decreases with the increasing negative charge. Of course, because when you go to try to pull an H off of something that's already negative, you're trying to remove a positive from something that's negative. That's a lot harder, right? Opposites attract. As you try to strip away this H and this becomes +1, this whole thing is on its way to -2. So that's going to be harder to do than it is to take the first one off. So the second H is always much harder to remove than the first one. Another way to say that is if there's two H's on there, everything else being the same, these are both SO4, two H's and no charge. This one has one H and a charge. This will be the stronger acid. Okay. Another example of that, we could do a real quick one. Here's two candidates. I want you to tell me which is stronger. This is carbonic acid. This is hydrogen carbonate. Which of these two things is stronger? This one's stronger. The one that is less negative already, because for this one to react, I've got to pull just one hydrogen off and make HClO minus O2, HCO3 minus 1, which is just this guy. This guy, I've got to pull the second one off to make another H. That's hard to do. And CO3 minus 2 to make carbonate. Okay, so this guy over here is a much stronger acid. Right? It's usually about like 1,000 times stronger, 5 orders of magnitude. So 4 orders of magnitude, 3 orders of magnitude is 1,000 times stronger. 4 orders of magnitude is 10,000 times stronger. So that's what you usually see. Okay. So let's take a look. Now, this example, this is at the bottom of page 10. This could be in a multiple choice question, right? You're going to have to put together all of the different rules that we just learned, right? So back the trends about the binary acids on page 9, the oxy acids at the bottom of page 9, and the top of page 10. Those 3 rules are going to go into determining which is stronger, okay? So forget that I have the answers underlined, the answers circled, right? Let's pretend that we were starting and they weren't circled, okay? So which member of each of the following pairs is the stronger acid? Okay, so everything is the same here. These are binary acids. Remember, they're not acids at all, this one especially, okay? So as you move down the periodic table, the acid strength gets greater for the binary acids. So phosphorus is underneath nitrogen on the periodic table. Here's the periodic table, right? So they're in exactly the same group of the periodic table, but phosphorus would be stronger than nitrogen because it's a bigger ion. So pH3 has a little bit of acidic properties, and we said NH3, not only does it have very weak acidic properties in the traditional sense to give off an H plus, it actually turns out to be a base for a totally different reason. So question A, which is stronger? pH3. Okay, let's do B. B is also binary acids. So I have HI versus H2TE. Okay, so let's check out where I and TE are on the periodic table. This is tellurum and iodine. Okay, so what did we say? The more electronegative the element is, they're in the same exact row of the periodic table, so it doesn't have much to do with the size. But iodine is further to the right, right? So it's a little bit closer to fluorine. So I would expect HI to be stronger than H2TE because I is more electronegative than tellurum. That comes from the second rule on page 9, this rule here. Okay. All right, what are we up to? C. All right, this is a really easy one. Okay. I have 2 identical polyatomic ions, SO3, right? Well, remember the name for SO3? So SO4 is sulfate, so this is sulfite. Okay, so if I have 2 H's on it versus 1, it's much easier to remove an H from this than it is from this, because here, remember, I'm trying to pull an H off from something that's already negative. That's not going to be easy. So this guy is more acidic, right? What does it mean to be more acidic? The ability to give off H pluses. This one has a greater ability than this one. Okay, next one. All right, between these 2 acids, okay, they have identical structures, right? They both are the acids that come from polyatomic ions of astatine. Okay, so I'm saying that right, right? And, oh, sorry, arsenic. Okay, so they're both the acids that come from arsenic. This one has 4 oxygens. This one has 3 oxygens. Okay, so the more oxygens you have when everything else is being the same, the stronger the acid you are. Okay, all right, last example, E. Everything's the same. Both of these have a -1. Both of them only have 1 hydrogen. So I'm not comparing the difference between two things where one is the negative and the other one is neutral. So what's the difference here? I'm just changing the element between sulfur and selenium. And we said more electronegative, the more acidic you will be. So where's sulfur? Sulfur is closer to fluorine, right? Here's selenium. So sulfur is more electronegative. That's why this acid here, okay, that's why this acid here would be weaker than this one. Sulfur's version would be stronger. The sulfur version would be stronger because sulfur is higher up on the periodic table. Good? All right. All right, so that gets us through all of these trends in the periodic table that you're responsible for. Okay, so the next topic that we're going to talk about is the Lewis concepts of acids and bases. Okay, and we kind of alluded to a little bit before because a great example of a Lewis base is the ammonia molecule. So that's the example that we'll use. Okay, so our third definition of acids and bases, we have an Arrhenius acid and base, right? We have Bronsted-Lowry acids and bases. And now we're going to have the Lewis concept of acids and bases. So what is a Lewis acid? A Lewis acid is a species that can form a covalent bond by accepting an electron pair from another species. So it is going to be an electron pair acceptor. A Lewis acid is something that accepts an electron pair. A Lewis base is a chemical species that can form a covalent bond by donating an electron pair to another species. So an electron pair donor is a Lewis base. Now, here's some examples. Let's go through a classic example and then we'll talk about why. Now, I don't want you to think of this as oxidation and reduction. We're not actually removing the electrons from anything. We're not sending them flying through the air or through an electric circuit. All we're doing is using them to make a bond. So if I have a naked proton, right, doesn't have any electrons at all, this is called a hydrogen ion. Okay? If I had a hydrogen ion in the gas phase, so there's no water around, and there was ammonia, NH3, then the following reaction would happen and its equilibrium constant would be close to infinity, right? Because this reaction would really go all the way to the right. All right, so this electron pair, if you remember when you learned about the Lewis structure of ammonia, ammonia has this wonderful electron pair that's free to react with other things. So this electron pair, which doesn't have anything bonded to it, would donate in to this proton that doesn't have any and make the ammonium ion. Now, the cool thing about this is originally this hydrogen is the guy that's going on, but once it goes on, it's indistinguishable from the other three. The bond strengths between this one, this one, this one, or this one would be identical. So if it was going to come back off, there would be an equal likelihood of any one of the four coming off. Okay, it's not like it's in a union and it says, well, I work here longer than you, so you lose your job, you get fired first because you're the last man in or the last person in. That doesn't work that way with molecules. So this electron pair is going to be the Lewis base, right? It's the electron pair donor. It's donating into something that needs them. And what's the Lewis acid in this case? The hydrogen ion. Okay. All right. Let's take another example here. Here's the oxide ion, and it's going to get together with the molecule sulfur trioxide. Okay. So if these two species were around, where's the extra electron pair coming from? Well, this oxygen has got four equivalent lone pairs. It's very stable. It would donate directly into the sulfur atom. One of this double bonds on here, right? See, this one down here is single bonded. This one over here is single bonded. That double bond, one of those electron pairs would pop back out to the other side. So these guys would, remember, see the four dots in there? Two of them would move back out to oxygen, which right now only has two lone pairs. The product is going to wind up with an oxygen with three lone pairs over here, and then this sulfur came in. So this guy If I didn't draw it with dots, but I drew it with lines, looks like this. Okay. Everybody's happy. Everybody has an octet. That's sulfur trioxide. Well, here comes the O minus 2, the oxide. One of these lone pairs kicks into the sulfur. And now if something else didn't happen, then there'd be 10 electrons around sulfur, which isn't allowed. So this guy pops back out, and I wind up with my sulfate ion, which is enormously stable. Okay, all right, so who's the electron pair donor? Oxide. Who's the electron pair acceptor? Sulfur trioxide. Okay, the last one is pretty cool. This is what happens typically to metal ions when they are dissolved in water. So uh, if I could dissolve up some aluminum foil and make aluminum ions into solution, which I could do, it's a little hard to do, but I can do it, okay, in a very strong acid, then 6 water molecules would hydrate the aluminum. Well, guess what's going to point in towards the aluminum metal since it's positively charged? The lone pairs, these lone pairs over here. Okay, so one set would kick in and smush in to the aluminum +3 on one side, and that would also, let's say that happens on the right-hand side. Same thing, another water molecule up at the top, another water molecule on the left-hand side, one at the bottom, one in front of the backboard, a blackboard, in this case my piece of paper, and one underneath. So that's our typical coordination is 6, right? Because there's 6 spaces, front, back, top, bottom, left, right. So here's the product, right? It would be hexa-aqua aluminum 3, right? There would be 6 water molecules, and those electron pairs would be what was pointing into the aluminum. Okay. Well, who's donating the electrons? The water molecules. So they are the base. If you are an electron pair donor, you're a base. If you're an electron pair acceptor, like the aluminum +3, you are an acid. Okay, last example. Okay, so this is it's called boric acid. It sometimes is written like this. Okay, H3BO3, but that doesn't do it justice because that makes it look like it's a traditional Bronsted-Lowry acid, like it's going to donate a proton. It doesn't do that at all. Okay, so what happens to it is that the boron actually is in a very unstable state. Okay, it doesn't have a lone pair. It's a boron with 3 single bonds to it, one coming straight across to an OH, another one to another OH that kind of sticks out of the blackboard a little bit, and one back behind it. So if you wanted to think about it, it's kind of a little bit of a kind of a triangle, right? So you have a triangle shape, okay? And then it has a lone pair, excuse me, not a lone pair, it has a pure p orbital that's on the top and the bottom that was never used in the hybridization because the hybridization was just sp2. Okay, well, this is going to be very reactive. If you take boric acid and you throw it into water, it's going to react with water in the following way. It's going to want to get an octet around the bromine. Remember, let's count the total number of electrons around the bromine. There's really just 2, 4, 6 around it. Okay, everybody's striving for 8. So if you put it in the presence of a Lewis acid like water, that lone pair from water can come in and donate into this pure p orbital, can take this space right here. Then it's going to change shapes from trigonal planar, from a little flat triangle, right? This is a totally flat triangle. If I was going to draw it to you in the other way, right, I'd have this, right? This guy's totally flat in the paper. And then if that's flat in the paper, coming out of the blackboard is the lone pair of excuse me, the p orbital, and back underneath is the p orbital, okay, down here and up here. Hard for me to draw in 3D, okay? So this is the way looking at the three bonds that are flat. This angle would be 120 degrees, 120 degrees. When you took Chem 1, how would you describe this? You would describe this as trigonal planar. And this is probably one of your examples. Well, after it reacts, the boron now has four single bonds to it. So four things wrapped around one thing goes into a tetrahedral shape. So here's the borate ion. When that OH comes in and donates, it loses a proton from the other side because now this guy can't break the octet rule. So if those electrons are going to make a single bond to boron here, then it's going to take one of those uh, two H's is going to get ionized and go off as H plus. Okay, so the reason why water is the Lewis acid here is because it's an electron pair donor. Subsequently, what we learned when we learned about Arrhenius acids is anything that when you donate it into water produces H plus is an acid. So boric acid from the Arrhenius perspective is an acid because I blindly throw it into water. I have no idea what's happening to it. And I check the pH and the pH is low because it's going to donate H pluses. So that's why it's an Arrhenius acid. But underneath, structurally, what's happening in this chemical reaction has nothing to do with H pluses. Okay? It has to do with this pair of electrons donating into boron to make borate and kick out the hydrogen ion. Again, so to review, we're going to finish up now. This is going to turn out to be a 30-minute video, which is perfect. Okay, to review, what did we learn? We learned a new kind of acid base theory is called the Lewis acid base theory. And the definition of a Lewis acid is an electron pair acceptor. And a Lewis base is an electron pair donor. Okay. Uh, So here's borate. Borate is the Lewis acid because it's an acceptor. Here's water acting as a Lewis base because it's an electron pair donor. Good. Okay.